Hey everybody, Mr. Troy here. I'm here for your first lesson of PreCalculus and your first lesson of the polynomial functions unit. Today we'll be talking about operations on complex numbers. Now, depending on what you've done for Algebra 2, you may have some experience with this, so you may think it's easy, but make sure you go through the video and have all of the important things down. So we're looking at two essential questions today. How do you perform basic operations on complex numbers? And how do you use the conjugate of a complex number? So what is a complex number? Well, a complex number is any of the numbers that you've used before, including real numbers, like my favorite, 17, pure imaginary numbers, like 4i, that letter we use, and imaginary numbers that may have both of those parts. So, for example, 17 plus 4i. Now, this is something that's often confusing to students. A complex number is any of these. So, it's not like a Venn diagram that anything with an I is a complex number and anything that doesn't have an I is not. All of these are complex numbers. For example, we could say 17 plus 0i, or 0 plus 4i, and we'd see that those are all in the same format. More on that in just a second. Remember that that I that we're using represents the square root of -1. So our definition for a complex's number is any number with a real and or imaginary part. Our standard form notation is to write the real part first and to write the imaginary part second. If you are using a program like WebAssign, you will need to remember to put your answer into standard form in order for it to be correct. Now, an imaginary number is any such complex number where b does not equal 0. So this could be something like 1 plus 2i, or simply -3i. That notation that we're using is I for the square root of -1. Now, you may remember the imaginary number cycle from Algebra 2, where you learn that by definition, I to the first power is I, or the square root of -1, and I squared removes the square root, so it is -1. So what happens if we continue to go up through our powers? Well, I cubed would be I squared times I, or -1 times I. So I cubed is the opposite of I, or negative I, as it's often said. Well then, I to the fourth, in the same manner, would be I squared times I squared, just by using our regular properties of exponents. So that would be +1. If I take I to the fourth times I would have 1 times I, which is I. And we notice that we get this same pattern over and over again, which is another nice reminder that anything raised to the 0 power is 1. This pattern can really save us some time. because we can see that if we divide the exponent by 4, the remainder indicates where we are in the cycle. Now, how did I know to divide by 4? Well, I see groups of 4 here repeating in the cycle. And I know, for example, if I do 7 divided by 4, that's 1 with a remainder of 3, which gets me right back at this. So if you were asked, for example, what is I to the 57th power, you could use that little trick. So when you do 57 divided by 4, you get 14 with a remainder of 1, which is how you know that it is I to the first, which is I. So a question when we get these building blocks is, what do I do with them? How do I add them? How do I subtract them? Etc. Adding and subtracting complex numbers is simple. You add or subtract the real parts to the real parts and the imaginary parts to the imaginary parts. You're using their coefficients. So for example, for problem 1 here, if I want to do 3 plus 4i minus 5 minus 3i, I'm really just having to think about 3 minus 5, which is negative 2, and 4i minus negative 3i. Those combine just the way any other variable terms would. So 4i minus negative 3i would be positive 7i. Remember, our standard form is to write in a plus bi. In our second problem here, we start with negative 3 minus negative 3. Something minus itself is 0. 2i plus negative 4i minus negative 3i. 2i plus negative 4i minus negative 3i. So our answer for that one is just I. When it comes to multiplication, you want to use the distributive property, or perhaps you've called it foiling in the past. For example, here on problem 3, we would distribute the 2 and the negative 4i to each of the two terms grouped in the second set of parentheses. And using that foiling pattern that we learn in Algebra 1 or pre-algebra, we would get 6 plus 6i minus 12i minus 12i squared. Now the reason I wrote that minus 12i squared there is, remember that I squared equals negative 1. So this negative 12i squared is actually the number positive 12. So this is really 6 plus 6i plus 12 minus 12i for a grand total of 18 minus 6i. Now, I prefer to stack when I distribute, as I showed here, but you don't have to do that if you don't want to. Just make sure that it's written in standard form when you're done. For our next problem, we need to remember that when we are squaring a thing, that means multiplying it by itself. And while there are shortcuts to squaring things, perhaps our best option, if we don't know those shortcuts yet, is to write it out as two binomials here. So give that one a try yourself. When I FOILed, I got 16 plus 8i plus 8i plus 4i squared. Now remember that this I squared is negative 1, so this is actually negative 4, the pure real number, which gives me 12 plus 16i. Our last operation is division. And with division, we are going to treat this like rationalizing the denominator. So for example, if the problem that you were trying to do was 3 plus 4i divided by 8 minus 2i, you would think about this fraction and then rationalizing that denominator. Now, why isn't that denominator rationalized already? Well, it has an imaginary number in it, which after all is the square root of -1. So how can we get rid of it? Well, we have to use what's called the complex conjugate. So complex conjugates are numbers in the form of a plus bi and a minus bi. Now, quick warning here is that only the imaginary part changes. So if you were asked to multiply 3 minus 5i by its complex conjugate, you'd be doing 3 minus 5i times its conjugate, 3 plus 5i. Now, multiplication is commutative, so it doesn't matter which order you write that in. Here's the interesting thing. When we FOIL this out, we get 9 plus 15i minus 15i minus 25i squared. The imaginary parts cancel out, and this I squared, remember, is -1, so this really turns into 9 plus 25, which is just 34. So when you multiply a number by its complex conjugate, the imaginary parts go away, and you are left with a pure real number. It's for that reason that our first two steps to rationalizing a denominator is to determine the conjugate and then to multiply the top and bottom by that conjugate. Now, when we say determine the conjugate, we are talking about the conjugate of the denominator. So in this case, that would be 8 plus 2i, which we are going to multiply by the numerator and the denominator. The reason we're multiplying both the numerator and the denominator is because we're treating this as a fraction, which means in order for it to keep its same value, whatever we do to the top, we must do to the bottom as well. Now, a common mistake for students here is forgetting to FOIL. A lot of people will just want to multiply the 4i through as opposed to the 3 plus 4i. So if it helps you, you might want to use parentheses around your terms. You don't need to as long as you understand. Okay, so we're going to do that. Based on our last example, we would expect the denominator to become just a real number. Now, after I do this, I need to simplify. So for example, remember once again that this 8i squared really counts as -8. So that would give us 16 plus 38i in the numerator and 68 in the denominator. Now, our last step is to write in standard form, which is something that is often forgotten. We're supposed to write a plus bi, not a plus bi over something. So, for example, we would start by saying that this is 16 over 68 plus 38 over 68i. And then, if we have the need to, we will reduce. So this simplifies down to 4/17 plus 19/34 I. Another way that this problem may be worded is simply to say write in standard form. In that case, you would just rationalize the denominator. I'll show that here. I determined that my conjugate of my denominator was 2 minus 2i, and I'm going to multiply both the numerator and the denominator by that. For my numerator, I get 6 minus 8i plus 2i squared, And since this 2i squared is really 2 times negative 1, I get 4 minus 8i for the numerator. For the denominator, I get 4 minus 4i squared, which is 8. And I'm going to write this as 4/8 minus 8 over 8i, which simplifies down to 1/2 minus 1i. You may not need that intermediate step, but it's there for you if you do need it. Thanks for watching. Hope that was helpful.